Bueno, nuestro primer presentador de la tarde es Pim Van Pelt, a quien le tenemos que agradecer mucho que haya venido porque estaba malito hace pocos días y lo ha podido combinar para venir a hacer la presentación esta tarde, o sea que hay que agradecerle que haya podido venir a pesar de los problemas. Y nos va a hablar de VPP o de cómo tener un router con una sola dirección IP versión 4. In English, I guess, Pim?
I guess.
I guess, ok. Pues vamos a practicar inglés para empezar la tarde con buen pie. Y nada, the floor is yours. Thank you.
Oh, thank you very much. Before I start, I hope everyone had a good lunch. I need to take a selfie because I put a picture of everyone who presented so far on Mastodon, so I guess I need to do that myself as well. You could smile. Thank you. Excellent. I'm going to try to get this done in 30 minutes. I understand that you would like English speakers to speak slowly. Yeah, you're shit out of luck on that one, because I'm going to go pretty fast. First, a little bit of introduction. This is about a software router called Vector Packet Processing, also known as FIDO. It's in the Linux Foundation. I'll talk about it a little bit. It's a practical conversation about my ISP and how I removed the need for transit point-to-point networks in the backbone. So by means of introduction, my name is Pim. I've been a member of the RIPE community since the mid-90s. RIPE 34 was the first one that I went to. You can reach me at pim@ipng.nl. I sound American, but I'm actually Dutch. And I live in Switzerland, so since 2006 I got the obligatory IPng.ch. In case you didn't know this, IPng stands for IP Next Generation, which was the code name of IPv6 when it was in development in the IAB and the IETF back in the 90s. In the pandemic, I got incredibly bored doing homework, traffic, going to my basement, and then having a bunch of meetings, and so I incorporated IPng into a limited liability company that has 0 employees. We are a developer of software routers. That's what we do, based off of Intel's data plane development kit and vector packet processing. We're an absolutely tiny operator from the town of Brüttizellen in Switzerland. And if you haven't heard of this, that's okay. Most Swiss people have also not heard of the town of Brüttizellen. So the top left here is the network in and around me in Zurich. And then the network down below is maybe a little bit more well known for most of you. There is a ring that I operate from Zurich to Frankfurt to Amsterdam, the north of France called Lille, and then Paris, Geneva, and then back through a couple of cities in Switzerland to my hometown of Zurich. These are 14 of these fully open source routers running Debian and vector packet processing. We have, it's a little bit of an undershoot, 2,350 or so BGP adjacencies. We appear on the flap, except for us the L is Lille, not London, but I think it counts because it starts with an L. And we have a 4-digit vanity AS number. If you've heard of 6-access and IPv6 tunnel broker from back in the day, I operated that thing. And in the corner, gathering dust was this 4-digit AS number, so I took it over. A quick introduction on vector packet processing. It's an open source, completely open source tool. You can download it from GitHub and from the FIDO website. It runs in user space, not in the kernel. It provides super fast networking. It's a data plane that uses libraries like the data plane development kit, RDMA, remote DMA, VirtIO, VMXNet if you have VMware, AVF, enfin, a bunch of other libraries as well to get the packets off of the physical network card. And it easily exceeds 100 million packets per second and 100 gigabits of throughput. In fact, 10 times that has been done in practice. So a terabit and 1 billion packets per second. And it runs on commodity hardware. So just your Dell, your HP server that you rack with a bunch of network cards, it'll run there. So I first started working as a software engineer on VPP in 2021, having helped contribute the Linux control plane plugin, and I'll get to that in a second. And that adds the ability for this data plane to speak BGP, OSPF, ISIS, VRRP, SNMP, all the things that you would expect a router to have. This talk is about some changes I made to VPP and to Bird, a popular routing suite, to be able to route traffic through interfaces without any IP addresses. And if you've been around for a while, we used to always do this back in the day with ATM networks. We'd have unnumbered interfaces, and that is what this is perpetuating back in VPP and Bird 2. So how does this work? When you create a VPP router, it will take away all your network cards. So what you used to have before, ETH0 or ENS3, the thing is gone. And it's bound now by the user space process in VPP. And the Linux control plane plugin puts it back. So with this tool called VPP-CTL, you can create an interface in Linux called ICE0, plumbing it from the data plane interface called 100 gigabit Ethernet 400. And that thing then shows up in Linux, and you can manipulate it just like you would any other interface. So you can give it an MTU and some IP addresses, maybe create a sub-interface on it, a VLAN with tag 101, give it a name like IPng, and then as well some IP addresses and some defaults, and then you can ping ESNOG.net. So what happens now is the ICMP packet goes from Linux kernel through this TUNTAP device into the data plane that sends it out into the internet, and when it comes back, we know that it's destined to an IP address that you put on the router, and so it copies it back into the tap so Linux kernel sees it. And as a result, all the traffic that goes through the router, east-west, is not seen by Linux at all, only the traffic that goes to the control plane. That's why this thing is called the Linux control plane plugin. Who's heard of Babel? 1, 2, 3, 4, 5. Okay, 5 people. I had heard of Babel before, but I'd never really dived into it, so don't worry if you don't know it. It's an IGP, not too dissimilar from something like OSPF or ISIS. You use it to exchange routing information between nodes in a network. So I turned this on with Bird. Bird has an implementation of Babel which is pretty mature. It's meant to build mesh networks on wireless, but it works as well on wired. So in this case, I configure Bird to turn on Babel on all the interfaces that start with an E, hence the E star in this, in this slide. And I turn on IPv4 and IPv6 on the Babel protocol. And soon thereafter, it forms an adjacency with some neighbor that it found on, in this case, E1. And then it starts exchanging routing information. And so, well, that already works. By the way, this is a Babel instance running in Bird on a VPP machine, right? Not just a normal Linux machine. It formed an adjacency, that's good. It then also learned a bunch of prefixes from its neighbor. And by the way, in my slides, you'll see everything in light blue is what I want to sort of draw the attention to. There's a lot of information on these slides. But in this case, I've learned an IP address 192.168.10.1 from some peer, right, on Babel. And I've also learned some IPv6 stuff, which is not too controversial. You'll just see this next hop 200::1, this one here. It's learned. It's an IPv6 one. Its next hop is link local. This is totally normal. That would be as well the case with OSPF v3. But I also learned this IPv4 next hop on an IPv6. Now, who knew that you could actually have IPv6 next hops for IPv4 destinations? By show of hands. There are 2 people that knew this, so that makes 3 of us then. It's a super cool trick, actually, that IPv4 brokers don't want you to know. And it also programs the FIB, so the forwarding database. Forwarding databases as compared to routing information bases, RIB would be in memory of your routing process, like on your Cisco or on your Juniper, or as well on your Bird. When you decide which next hop you want, you program the next hop into either an ASIC, or in this case, we program it into VPP. And looking at the VPP FIB shows you all this information, and here as well we can see there's an IPv4 via an IPv6 next hop on this interface called Gigabit Ethernet 10.0.1. And so that's good. The FIB is programmed. We should be off to the races. But it doesn't work. That was unfortunate. You can trace packets through the data plane, and in this case in red you can see these packets are all being dropped because VPP is claiming you didn't enable IPv4, you gave it no addresses, and so this is invalid, I'm going to drop the packet. So my first attempt to fix this was to force enable IPv4 forwarding on all of these interfaces. And there's some good news and bad news. The good news is it worked. So I can now ping and trace route through these machines into some other destination behind it. But the bad news is no intermediary nodes will respond to ICMP because they don't have an IP address, right? And that's not only aesthetic. So for a trace route, it could be annoying if you didn't have the next hop, right? But for path MTU, you really need the ICMP error message to be able to learn what the MTU was of the offending interface that could not forward. And so this is actually a pretty big problem. Now, my second attempt was to set interface unnumbered. And what you do here is you borrow an IP address from another interface, typically a loopback interface, and you put it on the transit interfaces, right? And so I now have E0 and E1 both carrying the 10.2, borrowing it from the loopback. And then forwarding broke. So that kind of sucked. So I'm still learning everything, and I'm still trying to program the fib, but I see these errors in VPP that the IPv4 source address is not local to the subnet that I'm on, which is not unsurprising because I have a /32 and a /128 IPv6 that I borrowed from loopback. There is no one in my subnet, right? This is a single host address. Okay, so my third and final fix was to keep the unnumbered interfaces, but to inhibit learning of these addresses in Linux and fixing the ARP issue by allowing ARP requests that come in that VPP called offlink to just respond to them regardless. Every OS does this. Linux, FreeBSD, Windows does this. All the routing OSs do this as well. And so from now on as well, with this change in, VPP does it as well. Good news, now ICMP responses work in the intermediary nodes. You can see the trace route here goes through 10.1 and then 10.2, the two routers in between, and 10.3 is the thing that I was trace routing. And I still have IPv6 next hops with Babel. Right, so now I've made IPv6 Babel work with VPP in the forwarding plane. And what we get now is a control plane, of course, that's pretty flexible with Bird, but a data plane that's really, really fast, that does hundreds of millions of packets per second on a PC. Problem is I don't run Babel. I run OSPF. Most people would run either OSPF or ISIS. I'm in the OSPF camp. So I thought as well I would look at OSPF and what does it do. And it turns out there is an RFC, 5838, which I think is a terrible RFC, and I'm not too ashamed to say it. It means to give the ability for an IPv6 session that is over link local to exchange IPv4 information in the routing plane. And I'll quote a little bit as I facepalm here. Although IPv6 link local addresses could be used as next hops for IPv4, which is exactly what I did with Babel, it's desirable to have IPv4 next hop addresses, which I don't necessarily oppose. So what we do is we will advertise IPv4 in the link local address field in the link state advertisement by placing the IPv4 address into the IPv6 field and zeroing out the top 96 bits. This is absolutely terrible because it means it fundamentally breaks any ability to use OSPF v3 with IPv6 for IPv4. So they really should have said, instead of could be used, they should have said can never be used for IPv6 next hops. However, there are very smart people on the internet. Ondrej is one of them. Ondrej works on Bird in the Czech Republic, and he found a very clever solution when we discussed this on the mailing list. And what he did in Bird 2 is create a new function called update loopback adder. And what it does is it scans the system for all IPv4 enabled interfaces, preferring those that have /32s, like loopbacks, otherwise OSPF stub areas, and if not that, any old IPv4 address that I can find. So it takes this, preferably a /32, and it sticks it in that wretched field, the link LSA field for RFC 5838, and it just works per normal. And instead of having the IP address on the interface, I'll sort of borrow it from another interface, a stub or a host address. And then all the routes that we learn are now on link because there's no one to ARP to in my local subnet. There is none because these are /32s. So actually this is a match made in heaven. Like the Bird 2 change that Ondrej committed with the Garrett that I committed in VPP allowing ARP resolution to work, and the changes that I made to the Linux control plane to inhibit these borrowed IPv4 and IPv6 addresses from making it into the Linux control plane, will allow for exactly one IPv4 and IPv6 address on loopback 0 to be shared on all interfaces in the machine, with OSPF v3 working for IPv4 and IPv6. And as a bonus, if you use forwarding detection, BFD, you can now share one session because you'll have IPv4 and IPv6 adjacencies all use link local IPv6, which is operationally cheaper on your router because you need less BFD sessions. So what that would look like is this. This is a VPP machine where I turn off this feature to sync unnumbered by disabling it. And then I'll give an IP address to loop 0, an IPv4 and an IPv6. And then I'll set gigabit Ethernet 10.0.0 and 10.0.1 to just borrow that IP address from loop 0. And because I've inhibited the propagation, in Linux we see E0 and E1 only with link local. Then I'll add one BFD session on any interface that starts with an E. And then I'll add two OSPF v3 sessions, one for IPv4, which is not very usual, and the normal one for IPv6, which was already there. The only difference here is that OSPF version 3 called OSPF 4, the top one here, has enabled itself for channel IPv4. So it's intended now to use RFC 5838 that I described before to exchange routing information over IPv6, but about IPv4. Adjacencies form, that's really cool. I can see two router IDs that I have a full point-to-point adjacency with using IPv6 link local. That's good. I am learning IPv6. I already was before, so I'll skip that, but I'm also learning IPv4. And I can see here that my neighbor 10.3/32 has learned unicast via itself 10.3 on interface E1, and it's marked as on link because it can't be ARPed for directly in the network because it's a /32, okay? And my routing table in Linux looks the same, except all of these next hops are marked on link as well, so I know that I must ARP for this neighbor. And with that, the trace route looks like this. This is a 9,000 byte trace route through the VPP lab that I have, and it hits 10.0, which is the loopback of the first router, 10.1, 10.2. And for completeness as well, IPv6 trace routes, well, they worked before. I didn't change anything there, and they still work now, as well as showing the responses from IPv6 loopback addresses. And just for the record, you never needed IPv6 transit networks in the internet. I don't know why we all have /64 transit networks, but they were never necessary. You could have always used link local only. Okay, so with that, that works. So I played around with this a little bit, and I got the code committed, and some binaries built, and some other folks tested and validated it, and now I'm ready to roll it out in my own ISP. So my start situation here is each router has a loopback address, right? So for v4 and for v6. But then it also has one or more, typically two or more, point-to-point networks to sibling routers. It's a ring, right? So I always have an east and a westbound neighbor, and sometimes even more than that. And the upgrade game plan is, first I'll upgrade Bird and VPP because I need to pick up these code changes that I committed. This is an intrusive change, of course. It needs to restart the data plane. It's like rebooting your router, so it needs to be done at night in a nightly maintenance. But I'll take the opportunity as well to upgrade Bird and then to rename my OSPF 4, my old OSPF, to a thing aptly called OSPF 4 old. And I'll create an empty new OSPF 4, which is OSPF v3. And I do apologize for having to say v3, v4, and v2 so much. And then really all I have to do is move interfaces over one by one, right? From the old IPv4, which is OSPF v2, to the new OSPF 4, which is OSPF v3. And then I should be done. And at the end of it, I will have only one IP address per router. This is taken from my bash history, where I'm upgrading a machine called DDLN0. It's in a colocation site where I have two of these routers. So the first thing I'll do is I'll add 1 and a 0 in front of all the OSPF costs. So if the cost was 20 before, it will now be 1020, 1020. And then I'll configure Bird which means I'm draining the links and like other paths will be cheaper, right? So I'm going to avoid using this router for the time being. Then with that second sed command, I'll replace the name of protocol OSPF4 to call it OSPF4_old instead. Then I'll download some packages, in this case the bird package and the VPP packages that I've created. I will enter the data plane with the NSEnter, and then I will abruptly kill -9 the VPP process, and I'll stop VPP and bird. I'll depackage install the Debian packages for VPP and as well for bird, and I'll start everything up again. Now, if I do this on a Cisco IOS XR, like an ASR 9K, or maybe a Juniper, or maybe an Arista even, this actually takes quite a while. In VPP, it takes 92 seconds. So this whole thing, upgrading the data plane, restarting it, reinitializing it, finding adjacencies, full table load from 2 peers, is 92 seconds. And this thing is back up in the DFC, routing like a champ. Obviously still drained, so it doesn't have a lot of traffic, but the point is you can do an upgrade on a VPP machine in about 1.5 minutes. So now I'm still seeing this OSPF4 old, which is the old OSPF, and it still has its neighbors. Nothing has changed there. So I do this on each router one by one, and they now run the correct bird version and the correct VPP, so I can continue with the next step. And here what I'm doing is changing an interface that used to be called XE for 10 gigabit 1.1, which had an IPv4 and an IPv6 transit net. And I'll hash them out, I'll comment them out, and I'll say you're now unnumbered from loop 0, and I'm going to call you DDLN1. It's because that's the interface I'm pointing at the router called DDLN1. When you don't have IP addresses anymore on your routers, it gets a little bit difficult to find out who is pointing at whom. And so I can roll this out, and I can change now OSPF, as I said, by removing the interface from the old OSPF4 and putting it under its new name, DDLN1, in the new OSPF4, which is an IPv6 enabled one. So those are the 2 changes I have to do for every single interface in the network. And as I reload this, obviously as well on the DDLN1 router so they can form an adjacency, I now see that OSPF4 has one IPv6 adjacency where it is sharing its information with that other router. All the other routers are still in the old OSPF, and IPv6 did not change except for the name. It's now called DDLN1. Cool, but I learned my neighbor, DDLN1's loopback address is indeed .6 at the bottom of this screen, and I've learned it on the interface DDLN1, and it's on link, so this stuff just works. So now I need to rinse and repeat. I don't have a large network, but it's also not super small. So I need to go through all these 14 routers, all the interfaces, pairwise, upgrade them, right? Move it to OSPF v3, which, by the way, can coexist just fine if you think about it. OSPF has external routes, which it learned from someone else. It has E1 and E2 types. The E1s will always be preferred, so that's within my protocol. But if I'll not know where to reach my peer, but I know it from the other OSPF, I'll just call it an external E2. So that keeps on working just fine. It's a little bit fickle with the costs because costs don't transfer between E2 and E1. But if I do this sufficiently quickly, and I did this in one night, then it should be fine. So at the end of it, I go from just a couple of routers and a couple of links to like the Zurich Metro, and then all the way north up to Frankfurt, Amsterdam, and then back down through France and Geneva. And then the network is configured with this new protocol. And now we see as well the trace route for IPv4 is responding from loopback, right? The same as it was in the lab, except these are now live IP addresses. So each one of these routers will have typically only one IP address left. At the time that I did this, I had 27 point-to-point networks. So I got to return 54 IPv4 addresses that can be used more sensibly somewhere else than in transit networks. And as well, of course, the IPv6 /112s. So for me, having in AS8298 only 2/24s, that's actually that's a lot. Maybe I'll sell them on the black market. Okay, so is this thing fast though? This is actually the #1 question that I get when I talk about VPP. It's like, it's great, but you can also just use Linux. It was always there, or FreeBSD, right? Why would you use VPP? And the answer is because it's really, really quick. It's enormously fast. So I'm taking here this Dell R730, It is from 2016. I bought it secondhand for €600. It's a very cheap machine, really. It's 2U, and I'm going to put a bunch of network cards in it, and I'm going to put it through its paces. It's actually a longer presentation, but I'll try to condense it down so that I fit in the 7 minutes that I have left. So my lab setup here consists of 3 load generators. So these will be creating the packets. And then this big Mellanox switch, which is 48 times 25 gigs and 8 times 100, which, by the way, runs Debian. You should totally run Debian on your Mellanox switches. And then at the bottom there, you see this device under test, which has 24 10-gig ports. So it's 240 gigs total. Half of them are on the first CPU, and the other half are on the second CPU. If you ever do something like LS-PCI, all the PCI addresses that start with low numbers will be on NUMA node 0, and all the ones that start with high numbers, like 128 and above, will be on NUMA node 1. And what I'll do is I'll make sure that the CPUs on the NUMA node match with the network cards on that NUMA node, so that I don't have to use this QPI bus to transfer traffic between the 2 CPUs, because that's kind of a waste of bandwidth. So in T-Rex, it's an open source load tester built by Cisco, you can add source and destination MAC addresses on port pairs. And what it typically does is it starts sending traffic out one port through this cloud called the device under test, and it's expecting the traffic back on the other side. And if it sees the packet on port 1, then it was good, right? But if it didn't see that packet on port 1, then it somehow got lost in that cloud. So really, with this type of load testing, all I do is I send a bunch of traffic and then count, did I see the traffic on the other side? So this load tester here shows 4 ports. You can also as well have bigger load testers. But in my case, I had 3 load testers with each 2 port pairs, so 18 ports total. And I used 2 methods of load testing. Method number 1 makes VPP run on 1 CPU thread. So you must know VPP is multi-threaded, so if you had multiple CPUs, you can linearly scale up by adding more CPUs. And typically, modern network cards will have multiple receive queues in the hardware, so you can make one thread listen to Q0 and one thread listen to Q1 and scale that way. And because all the threads are lockless, it is linear scaling. If you had 10 times as many threads, you would have 10 times as much throughput. But to test what one CPU could do, I'll limit VPP to only run on 1 CPU, and then I'll keep on loading it until it doesn't go further, and then I know how many packets per second that 1 CPU can do. Method 2 then is just RFC 2544. You start at 0 load and then linearly ramp up to 100% of the line rate, and then see where did the machine stop forwarding traffic, or maybe even crash. There's an RFC for that, and I implemented that in a Python script. So method 1 looks like this. Cisco T-Rex has a textual user interface for us CLI nerds. And it shows you here at number 1 that there are 4 ports that are each transmitting at 10 gigabits. And then at 2, what I'm sending out is the packets per second and bits per second that I'm sending out. Number 3 is what I'm receiving on the other side, which should be the same number, otherwise it's getting lost somewhere in the middle. And then number 4 is all these detailed packet and byte counters for each port individually. And what I can see here is that this thing is doing 4 times 10 gigabits, 64 byte packets, which is the smallest we're allowed to send before they become runts. And it is forwarding 59.44 million packets per second. They're all coming out the other side. So I know that at least 14.88, which is the line rate of a 10 gigabit port, can be done 4 times by the VPP machine. That's a little bit of a spoiler there. But if it's at least 14.88, then how much is it really? So what I've done here is I created a table where I do 4 sort of typical forwarding techniques. One would be a layer 2 cross connect. The packet comes in on this interface, and I just want to send it out the other interface, do nothing with it. It's a bridge, if you will. And MPLS, and then IPv4, and then IPv6 forwarding. And at the top left here, you see that at 1,000 packets per second, I can count how many CPU cycles VPP is taking to forward that one packet. It's about 991. If I do 1,000,000 packets per second, this thing goes down pretty drastically. It goes 5 times better. So if I do 1,000,000 packets per second, each individual packet only takes 199. And if I max it out, I find that it does 15.3 million packets per second on 1 CPU thread, There are 44 CPUs in this machine. So for this particular operation, the total capacity of the CPU would be roughly 600 million packets per second. 600 millones. So MPLS does 10.3 million packets per second. IPv4 does 11.1 or so, and then IPv6 does 9.7. The fib lookups in IPv6 are a little bit more complicated. But it's still plenty good. So I'll make two claims. Claim one is, can it do 100 gigabits? And so for that, I'll turn on 18 ports and just ramp them up from 0 to 100% of line rate using very large packets, like 1,514 bytes, typical Ethernet frame size. And at 9:50 in the morning, I achieve 100 gigabits of throughput, and at 10:12, 180 gigabits. That's like as much as you can do with 18 10-gig ports, yes? And that's roughly 14.7 million packets per second. The bottom graph that you'll see here is the CPU load per thread, and they're down here. Like, they're doing nothing. They're absolutely bored. Note this thing has 44 cores. I'm using 2 for the OS. That leaves 42 left. Right? So I have 18 in use, which means I have 24 CPU threads that are doing absolutely nothing. They don't even run right now. They're idle. And because I only had 3 load testers, unfortunately, I can't show you 240 gigabits. I only had 18 ports to generate the load with. But it is proof that VPP would easily do 100 gigs. In fact, 180 is fine, too. A second claim is a little bit harder, like when you do smaller packets. In this case, I chose 128 bytes. Ask me later why. 128 bytes, you'll send a bunch more traffic, like 8 million packets per port per second. And here at 11:02, I've achieved 100 million packets per second, but the thing keeps on going up until about 165 million packets per second achieved, which is roughly 150 gigabits at 128 byte packets. And again, 24 CPU threads aren't even used. If I needed more capacity, I could have 2 receive queues for each network card and still have enough CPU, right? So even single-threaded with respect to each individual port, this thing easily does 100 million packets per second. Mind you, on a Dell 730, which is from 2014, so about 10 years old by now. That's what I wanted to share about VPP, using only one IP address in loopback for IPv4 and IPv6, and forwarding across Europe easily hundreds of millions of packets per second. Thank you for your time.
Thank you very much, Pim, and thank you for being so punctual. You just finished at the time you were supposed to. Thank you. Any questions for him?
I could imagine. Otherwise, I have a question, like if you want to take these pins off my hands, they're not coming back with me to, to Switzerland. There's an RFID tag on the back. You can scan it with your phone. Every week, there's another technical article from the IPng site.
Yeah. Question? Ah, no. Pensaba que era una pregunta. Question.
Thank you for saving me. Just
It's a very quick and easy question. Why unnumbered versus private addresses?
Yeah, I could definitely use private. I think it's kind of lame to have RFC19 show up in trace routes, essentially.
Yeah, not beautiful, but I mean...
Yeah, it would work. Absolutely, it would work just fine. In fact, there are many operators who do this. You can see this. And there's even more operators that forward this traffic through the internet, clearly, because you can see these addresses in trace routes. One thing that I will mention is, I didn't talk about it here, but my network actually is an MPLS underlay. And then I have point-to-point MPLS links for the VPP machines, if that makes sense. And so this whole network here is just disconnected from the internet. And it runs 198.19, if you've heard of this. It's like half of a /15 that's dedicated to VPCs. So I do that there. But I just figured you can avoid using IPv4 altogether. You may as well get with 2020s and stop using IPv4 altogether.
Yeah, and it's funnier, right? So.
And at least I have a story to tell.
Right, thank you.
Thank you.
¿Alguna pregunta más? Any question? Okay, then thank you again, Pim.